Welcome to this afternoon's Jones Seminar. While people are still getting settled here, I want to go ahead and do the introduction. It's my great pleasure to introduce Professor Fiona Lee, who is the William P. Harris Career Development Assistant Professor at Thayer School. Her BS and MS degrees are in chemistry from Nankai University in China, and she has a PhD in biomedical engineering from Washington University in St. Louis. She was then a postdoc in materials at Stanford University before starting at Thayer in 2016, where her lab focuses on the development of rationally designed functional materials, particularly for energy applications, and especially advanced batteries. She has more than 90 publications and has an astounding 27,000 citations. She's won numerous awards, including a Camille Dreyfus Teacher Scholar Award, an NSF Early Career Faculty Award, and an Air Force Young Investigator Program Award in 2017. So I'm very excited to hear her presentation today from her 6 years at Thayer School, and I'll turn it over to her.
Thanks, Charlie, for the great introduction. Can everybody hear me, especially the one in the back? Okay, thanks. It's my pleasure today to share with you my research since I joined Dartmouth in 2016. So my group has been working on next generation high-performing sodium batteries. For your reference, I'm still recovering from a pretty bad cold, so if please bear me for my coughing during the presentation, if there's any. Okay. Sorry. To begin with, I would like to use a couple of minutes to first give an introduction for my group's research. So I always call my group, we develop novel functional electrochemical materials for energy and sustainability. So we work on materials especially temperature resilient, cost effective, and safety enhanced. Currently, there are three main research thrusts in my group. The first one is we are dedicated in developing the next generation low cost and high energy sodium-based batteries. And the second research thrust is we're trying to develop a new solid-state electrolyte, especially based on the sodium battery system, and to try to replace the current flammable liquid organic solvent-based electrolyte in the current battery system. So for the third thrust, my group specifically, we develop batteries that can work for extremely cold environment, especially for military usage and for NASA space application. So this is a picture of the local community in Greenland. So we are also trying to develop a new energy solution for the Greenland community here. So in the following presentation, for today's presentation, I will mostly focus on the first part, the high energy sodium battery system, with a little bit touch on the battery for extremely cold temperature. Sorry, I forgot to mention, one of my very talented graduate students find there are actually both lithium and sodium in my English name and my last name, and also created this very interesting group logo. So I'm very proud of my student. I really like this logo because we are developing the next generation sodium battery, but we are not really abandoned lithium. Part of my group's research, we still work on the lithium system. Okay, so talking about battery, we always want to start with the current commercially available lithium-ion battery. So based on this graph, I think you are very familiar with lithium-ion battery now because everybody using your cell phone, your laptop, and especially the electric cars. Battery, like lithium-ion battery, also has been widely applied for military applications such as drones, and then for the space application. So if we look at the energy density that the current lithium-ion battery can deliver, the theoretical energy density around 400 watt-hour per kilogram. And this is, if we look at the reference here, this is back to 2001. But you still, even this is almost 2 decades ago, but there's really not much improvement in this graph in terms of the lithium-ion battery. So the practical energy density we can get is around 100 to around 260 watt per kilogram. So this is the best record on market right now. Okay, so let's look at, so I want to talk about why we start to work on the sodium-based battery system. There are some cost and sustainability concerns if we look at lithium. So if we look at these two charts, so we compare the lithium consumption, okay, in different applications. So if we look at the blue part, this graph compared to 2010 to 2020, so we will find that the consumption of lithium, okay, back in 2010, so there's 23% goes to battery right now. Back to 2010. But if we look at the 2020, it has rapidly increased to 71%, which make lithium-ion battery is the single largest end user of lithium. So if we look at the world lithium reserve by country, you will see that currently there are only 4 countries in the world that has abundant lithium. So only Chile, China, Australia, and Argentina. So this is U.S. is among right here of the other countries. And then so here I quoted some words from investment advisor. So we are really facing a total disconnect between the coming demand for lithium and the available supply. So this is actually the truth because if you ask my students, so they will told you that since last year we are actually it's very hard for us to actually purchase any lithium-based salt or lithium metal for our lab research. So our order has been back order for almost 6 months, and it's very hard for us to get lithium supply. So based on a paper published on Drew in back to 2018, so they calculate based on the consumption rate. So the residual lithium reserve on land actually will be exhausted by 2080. So this is actually not really far from right now. And also, this is there's another study show that the global lithium market it has been estimated to be double, okay, in the next 5 years. So here I want to show you the price of lithium raw material. As I just mentioned, if we look at this first graph here, you notice that since 2016 there is a rapid increase in terms of the lithium raw material. Is lithium carbonate price has been increased from 6,500 per metric ton to around 17,000 per metric ton here. And then there is a slight decrease in 2019. And during the past 2 years, I want to say it's a pandemic is doing some weird things. It keeps at this low price level. However, since last year, okay, so the lithium price has been skyrocketed since the early 2021. So it has been increased from around 10K per metric ton to almost more than 20 per metric ton. And this is the forecast of the lithium price in the future. So all these facts tell you that we do facing some cost and sustainability concern, and that's why my group will begin to work on the sodium-based system. So if we look at sodium is right below in the periodic table is right below lithium. So it has many similar chemical and physical property as lithium. So here is the abundance of sodium in the Earth's crust. So here is sodium is around 23 kppm, and this is how much lithium we have in the Earth's crust. It's 1,000 times more abundant of sodium than lithium in the Earth's crust. So if we compare the raw material price, as I just mentioned, so sodium is only in the range of 160 to 200 per metric ton. So I want to mention for this graph, it only shows you the abundance of sodium in the Earth's crust. It didn't even mention how much sodium we have actually from the seawater, right? Okay. So this actually echoes my talk pretty good. So this just released in last month. It shows the IUPAC is the International Union of Pure and Applied Chemistry. So they released the top 10 emerging technology in chemistry in 2022. The sodium battery is listed as the first emerging technology. So especially they want to highlight the potential of another alkaline metal, which is sodium. Also, the world's biggest manufacturer of lithium-ion battery, there's a Chinese company called the CATL, has recently revealed their first generation commercial battery based on sodium. So all these give us a lot of reason to work on sodium-based battery, but if we look at the conventional sodium-ion battery, however, I want to say that the conventional battery is not really an ideal alternative to the current lithium-ion battery. So the reason is relatively straightforward because sodium, if we think about it, its molecular weight, so it's already like 3 times heavier than lithium. So if we look at the conventional sodium-ion battery, it has similar chemistry, I want to say chemistry like the lithium-ion battery. It's called the intercalation, de-intercalation-based electrochemistry, which the sodium-ion will intercalate and deintercalate between the cathode and anode material during the charge and discharge process. So in this case, the maximum number of sodium, so similar to the current lithium-ion system, the maximum number of lithium, if you come back, think about this is a lithium here. So you replace lithium with sodium with a similar mechanism right here. So what you get is you do get a battery, we call it conventional sodium battery. However, you do increase the total weight of the battery system because sodium is heavier. So this is the practical energy density we can actually get from conventional sodium-ion battery. Is in the range of 100 to 150 watt-hour per kilogram. I want to remind you this number for lithium so can go up to 260 watt-hour per kilogram. So that is why sodium-ion battery is not really as competitive as lithium-ion battery to be used, especially for electric vehicle. So sodium-ion battery is more widely used for grid-scale energy storage. Okay. So in this case, if we really want to develop some high-energy sodium-based battery system, so we need to dig into some new battery chemistry. Okay. So here I want to show you, besides the conventional sodium-ion battery, so there are also other type of sodium-based battery system. So this is the conventional sodium-ion battery. And there's something emerging battery technology called the sodium-sulfur battery. So this is the theoretical energy density for this new battery system can offer. So you can see it's 1,300 watt-hour per kilogram. So it's much higher than the conventional sodium-ion battery system. So there are some also other emerging sodium-based battery technology. One is called the sodium oxygen, or sometimes this is called the sodium air battery system. And here I also list the theoretical energy density it can deliver, and also the sodium carbon dioxide battery. So you can see all these 3 types of battery systems. So they all have a much higher theoretical energy density compared to the sodium-ion battery, so which is less than 400 watt-hour per kilogram. So in this case, this gives us a reason that why we want to dig like all these new emerging battery technology and how we can really improve the performance of all these battery systems. So if we look at all these sodium-based battery system, one common thing for all these battery systems is the anode material. Okay, so they all use sodium metal anode, especially these 3 high energy density battery systems. For the conventional sodium-ion battery, you can also replace the current anode material with sodium metal. In this case, you can further boost the energy density of the conventional sodium-ion battery system. So that's why sodium metal is considered, we call it the holy grail, okay, of the sodium battery system, because it actually provides some, we call it the ultimate anode choice for the high energy sodium-based battery system. But if we look at sodium metal anode, okay, so why it hasn't really been commercialized, and why this anode is considered as still a dangerous anode material to be used as different type of sodium battery. So the main reason is because even sodium metal anode, it can provide a much higher capacity and a low electrochemical potential, and versus all the different cathode material. However, during something we call it the stripping and the plating process, we can transfer the language of the strip process. You can transfer this to a discharging process for the battery, and the plating process, this is the charging process for the battery system. So during the like stripping to the plating process, there is a series of challenges related with a sodium metal anode. So one one of the biggest challenges is during this charging or discharge process, you will have this unstable or we call it non-uniform solid electrolyte interface formed on the sodium metal surface. So this means that there is a thin layer of material, okay, during the charge and discharge process that you can form on the surface of the sodium metal anode. However, this thin layer is not very stable over the over the long-term cycling of the sodium metal anode. So, and this unstable SEI formed on this anode surface will cause different issues. For example, something we call the mossy and dendritic sodium formation, and then another thing is because sodium is very soft, so it has a much more severe mechanical property issue, because if you press it, so it can deform during the battery assembling process. Sorry, I forgot to mention that for this dendrite, why dendrite is dangerous is because dendrite is generally, we consider is a mossy or sharp dendritic structure, so it can actually penetrate the separator, and once these dendrites get contacted with your cathode material, you are going to get a short circuit of them, the battery system, and then it can cause a fire. Okay, so you have heard a lot of this battery fire from the news. It's mainly also due to the lithium dendrite. Lithium actually have a similar issue. The lithium dendrite can also form in the lithium battery system, which cause a fire. Okay, so that's basically, I summarized the issue I just mentioned. It causes a safety issue, and this can cause a we call it rapid electrode degradation. Another biggest issue is something we call the low Coulombic efficiency. So what this means is because sodium metal is is highly reactive, so once it interacts with the electrolyte, so it can cause some parasitic reactions, so which you can imagine that the energy you input in your battery, it doesn't really gives energy. Okay, so it actually transforms to some parasitic chemical reaction, so that leads us to something called a low Coulombic efficiency here. Okay, so how can we address this sodium metal anode issue? So if we look at how sodium, okay, is when we place a sodium interact with an electrolyte, so we always want a stable, if you recall, this is the SEI layer, the solid electrolyte interface layer, a stable layer formed between the electrolyte and the sodium metal surface. So in this case, we can do a couple of strategies here. So we can tune something in terms of the sodium metal electrode, and we can tune something in the electrolyte. All this effort we need to realize is to form a stable SEI layer between the electrolyte and the electrode. So during the past 7 years, so my group has developed a series of strategies, including we have developed some protective coating, which we can use as we call it artificial SEI layer to directly coat on the sodium metal surface. So in this case, we can improve the stability of the sodium metal electrode over the long-term cycling stripping and the plating process. And another thing is we also developed some solid additive. We can directly blend it with sodium, actually improve the mechanical to solve this poor mechanical issue of the sodium metal anode. And then we also try to control the sodium nucleation growth to try to manipulate the sodium plating process to achieve a uniform sodium deposition. Of course, we also work on the electrolyte formulation, and we Also try to find a stable matrix here. So what the schematic I show here is a porous carbon matrix. So we can directly actually infuse sodium into the matrix to further improve both the mechanical property and the chemical and the electrochemical stability of the sodium metal. So here I would like to use one slide, to summarize we have the effort I just mentioned. I divided into different sessions, so you can see we have done a lot of work. But due to the limited time of today's presentation, I'm going to give pick a couple of examples from here to show you how we really address the challenges of the sodium metal anode from using different strategies here. Okay. So when we first begin to work on sodium metal electrode, so the first thing we want to understand is what are the really difference between lithium and the sodium, okay? So because before us, there are already a lot of people begin to look at how to use metallic lithium metal as an anode material. So and we think, so what's the main difference here, and how can we borrow their knowledge to be applied into our research? So if we look at the atomic properties, okay, comparison between lithium and sodium, we can see that I want to point out here. So sodium has a much lower we call it first ionization energy, which indicates that the sodium metal is more reactive, so it's more easy to lose the electron. Okay. So in this case, this is the conclusion, so sodium metal is more reactive than lithium metal. So if we really want to design a good stable electrolyte interface, if we really want to make sodium metal work, we need a better design and control on the material property, because we really need to suppress this high reactivity of sodium metal with the electrode. So this is really more challenging compared to when we try to use a lithium metal electrode. Okay, I would like to start the example here to talk about the first work my group has developed since I joined Dartmouth in 2016. So this work is conducted by my prior postdoc, Dr. Weiyang, who is currently already a professor at Nankai University in China. So Dr. Weiyang she's an expert in synthesizing graphene-based material. So graphene is a very famous two-dimensional material. So at that time, we were trying to think of how we can take advantage of this expertise to try to synthesize a very thin layer of graphene material and try to coat the graphene on the surface of sodium metal to use this graphene material as artificial, we call it artificial solid electrolyte interface layer. So Dr. Weiyang has successfully achieved to synthesize the graphene to be precisely control the graphene thickness around 2 to 5 nanometer, and we will be able to control the level of defect, and we can also control the conductivity of graphene by controlling the synthesis temperature here. And since sodium is a good thing I want to mention for sodium has a very low melting point, so it's only 90 degrees Celsius. So we can actually slightly heat the sodium metal so that sodium metal can have a better interaction with the graphene, so we can decrease, we call it the resistance between this external coating material with the sodium metal electrode itself. So here is the experiment to show that we will be able to achieve a different thickness of the graphene layer. As I mentioned, that it can be controlled from just the 0.3 nanometer to 5 nanometer, and we give different names. So this is called the single layer graphene film, and the 2.3 is around 7 layers. So this is called a few layer graphene film, and we have this multi-layer around 15 layer thickness of graphene film. So I want to mention that the difference in the thickness you can see is very only in a very small nanometer range level, and later we find that this such a small difference actually make a really huge electrochemical performance difference in terms of the battery performance. So I also want to mention that the film is actually very rich in defects, so that why this is important is because you want the film to be, sodium ion to be easy to diffuse through this graphene film. Because if the sodium ion cannot move through the film, so you are not going to have sufficient ion transport. Okay? So here I want to show the electrochemical performance, since you're going to see a lot of these kind of curves in the following slides. So I want to spend a couple of minutes to explain what you are looking at here. So the way we test whether the graphene film works or not, whether it can stabilize the sodium metal electrode, is we use something we call a symmetric cell here. So this is a symmetric cell. We use a piece of sodium metal against another piece of sodium metal, and we put the electrolyte here, and we coat the graphene film on the sodium metal electrode. So in this case, you can see that there is really no cathode material here, so there's only anode material here. So in this case, we can completely eliminate the influence from the cathode, and we can also enlarge the issues for the sodium metal electrode by using this typical symmetric cell design. So what you are looking at here, the curve. So what is really a good curve is if the x-axis is how long time this symmetric cell is cycling, and the y-axis is the voltage. So here you look at is this range here we call the level of polarization. Okay, so the higher or the more spikes you see, is the worse the battery performance is. Okay, and then what we want to achieve is a decreased level of polarization, and we also want to have minimize the spikes. Okay, during the voltage spikes during the cycling performance. Okay. So here I just want to show you if we use a piece of bare sodium and compare to this, this is a field layer graphene coated sodium metal. So you can see we actually got a much more stable sodium metal cycling performance compared to a bare sodium metal. So this is another case if we cycle the battery at a high current density with a high capacity. So you can see the difference is more dramatic here. So, but we do find, as I mentioned, a thickness difference in only a range of 2 to 3 nanometer can have a critical role in the performance, because you can see that if, for example, when we try to cycle the battery at a high current, if we only use a few layer graphene, we prepared it, so it doesn't show much difference here. So in this case, in order to make the battery work, for example, at a high current or high capacity system, we really need to increase the thickness of the graphene film by around the 2 to 3 nanometer thickness level here. So in this, the conclusion for this work is in order to make the sodium metal system work, we need to make a more meticulously material design and control the material property in a more meticulous level so that we can achieve a desirable performance here. Okay. So here I want to show another image for this work. So you can see that this is after we disassemble the cell. So this is the surface of sodium metal. This is the one that covered by the graphene film. So you can see it's very flat. So for a bare sodium system, so you can see the surface is very rough. This also shows that the sodium metal is well protected by this graphene film design. So this is our first work. So after we work on this, you can see that the whole procedure, okay, so the synthesis and how we control the thickness of the graphene film is not really in a way that towards a real commercialization process, okay. So we begin to think, can we really find a faster way to really utilize this amazing material to prevent the sodium dendrite growth, but to try to eliminate all the complicated synthetic procedure we have we have in our previous work. So that leads us to our another work I want to use an example is in order to directly coat graphene, okay, on the surface of sodium metal, we begin to think about how we can control the sodium metal nucleation and growth process to directly to directly control the sodium metal to be deposited onto a very thin graphene film. So we call it a planar doped graphene to control the surface functionality of the graphene to try to directly realize a very smooth sodium deposition process here. So this work is conducted by my prior postdoc, Dr. Hu, who is already also now a professor in a university in China. Okay. So when we begin to start this work, we have some hypotheses that in order to control the nucleation and growth of the sodium metal on the graphene surface, so it must be related between some chemical interaction between the sodium atom and the graphene surface. So it might be related to the binding energy between sodium and the graphene. So by collaborating with Professor Yang at UCSD, so we have done some DFT calculation and to try to calculate the interaction between sodium atom and different plating substrate. So you can see here, based on the calculated binding energy, so our at that time our hypothesis is the higher binding energy we have, so the better interaction the sodium atom can plate it on the substrate, and we might have a better plating process. So you can see the calculated binding energy is some boron doped graphene is going to be has the highest binding energy compared to a bare copper substrate and compared to this pristine, which means undoped graphene surface, and also is higher than a nitrogen doped graphene. Okay. Experimentally, we have achieved different doping surface of the graphene, for example, including the one we calculated, the boron doped and the nitrogen doped. So this is the undoped, we call it the pristine graphene surface. But we do find experimentally there's always, as you know, that there are always difference between experimental result and your theoretical calculation. So experimentally for the nitrogen doped case, for the nitrogen doped graphene case, you will see that it actually has different type of doping form. So in this case, we have to really do some correction on the theoretical calculation to reveal the correct binding energy between specifically the nitrogen doped graphene case. Okay. So here is our corrected binding energy. So we have found that the boron still is the highest, and followed by the nitrogen doped one, and then this is bare copper, and this is the pristine graphene case. And then we try to see whether our experiment actually electrochemical performance actually match with the theoretical calculation to see whether our hypothesis actually works or not. So in terms of the performance, we do find that if you recall, I just show you how to you read all these graphs. For example, the smaller this voltage range here show you the lower level of voltage hysteresis, but here but some of you might see, oh, okay, here so it is really a low polarization. However, this means that the battery actually had a short circuit. Okay, so the battery actually died at this point because of the dendrite growth or the extra consumption of the electrolyte. So in this case, if we compare the performance, we will find that there is some inconsistency from the experimental compared with our theoretical calculation. So experimentally, we find the boron doped graphene has the highest stability, and then it's better than the nitrogen doped graphene, and then it's better than the pristine graphene, and then better than copper. So if you recall in the theoretical calculation, so these two are actually in the reverse case. So we further dig into the reason, we find that it's just because for the copper surface, for any commercially available one, after we purchase, we actually directly use the commercially available copper substrate, and the surface is actually relatively rough. So in this case, so this inconsistency could be probably due to the surface roughness of copper compared to all these relatively flat graphene coated surface here. Okay. So here I want to show another image. For example, if we look at, I specifically picked the boron doped one because this shows the best electrochemical performance. So I would like to ask your attention, especially for this, we call it the cross-section view of the sodium plating picture. So if we compare, this is a copper surface, this is a cross-section view of a sodium plated on a copper surface. So this is a cross-section view of sodium plated on a boron doped surface. So you can see this shows you a very packed and dense sodium plating pattern here. But if you look at copper, so this is a very porous or dendritic structure. So especially can be revealed from the cross-section view of the electrode here. Okay. So I just finished the previous showing you the previous work. This shows that we have done some series of work in trying to directly control the sodium nucleation and the growth process instead of just doing some coating on the electrode surface. Here I want to move to another example here. Is because when we begin to work sodium metal electrode, and we also want to compare the difference between lithium and sodium. As I mentioned, besides the chemical reactivity difference between lithium and sodium, if we look at the mechanical property here, okay, so you will notice that sodium is have much lower hardness compared to lithium. Okay, so this is also matched with our common sense that sodium is very soft and malleable metal. So if we look at the commercially available lithium or the sodium we can purchase from Sigma Aldrich, so this is, you can actually buy very well shaped lithium foil, okay, in this case. However, for sodium, so you will not get any of this a good well-shaped sodium. So what you mainly get is something like this. We call it the sodium cubes immersed in the mineral oil. And of course, the surface is slightly oxidized, but the internal part of the sodium metal is still pretty shiny. So in this case, give us an idea that sodium is more susceptible to deform and degrade during the electrochemical, especially during the battery assembly process, or also during the electrochemical cycling process. So in this case, so we think that it is more essential that we can actually find the ideal host material for sodium metal compared to lithium, because sodium is very soft, so we want to solve this mechanical property of sodium metal. So here I would like to use a couple of examples. So the first example first we begin to work on some copper-based matrix material because copper is widely considered as a good substrate material for battery anode material. So this work is conducted by my prior PhD student who already graduated last year, Dr. Wang. And Changlong actually find an easy way to functionalize a copper foam. So this is a porous copper substrate by two different methods. One we call the oxygen-treated copper foam. This is we call the sulfur-treated copper foam. So the treatment is very easy. So you just simply oxidize this copper foam for about in oxygen for 4 to 5 hours. And for the second case, we just use a sulfur system to sulfize the copper foam. And then we try to compare the surface structure of all these different surface-treated copper foam here. So this is an untreated case. So you can see this is for a sulfur-treated case. So the surface actually has some flour-like a flaky-like structure. So this is for the oxygen-treated one. So why we are doing this is because we are trying to infuse sodium metal into different matrix, and we find that after especially for the oxygen-treated case, we find that if we melt the sodium, because as I mentioned, sodium has a very low melting point, so we can easily infuse sodium metal into the oxygen-treated copper foam. So it can just instantly, we call it instant sodium infusion. However, if we compare to the untreated one, so the sodium doesn't really wet the copper foam surface. You can see the sodium droplet right here shows you a very poor wettability here. So in the middle, for the sulfur-treated one, it's actually kind of in the middle between oxygen or the untreated one here. So the reason could be due to that because the flaky-like structure give you a poor wettability angle. So that might be one of the reason that sulfur doesn't really work as good as the oxygen-treated case. So we got a uniform sodium distribution, especially for the oxygen-treated case. For the non-treated case, we have a discontinuous sodium infusion here. So the main reason is because the chemical interaction between sodium metal, when it interact with this surface-treated copper foam. For example, for the oxygen-treated one, we find that because sodium can actually react with copper to actually form a sodium oxide during the infusion process. For sulfur, it actually also form a sodium sulfide case. However, this for the sulfur case doesn't work as good as the oxygen case. So using this method, we'll be able to just very easily infuse controlled amount of sodium metal into a matrix material. So in this case, we can actually improve the mechanical property of sodium metal electrode. Okay, so after work on the copper-based electrode, we actually work on a series of different matrix material, which also include some carbon, three-dimensional carbon matrix material. We also functionalize the surface of carbon matrix compared to the copper, compare the performance with the copper-based electrode. And all these works, we find that we still try to work on controlled sodium metal deposition or infusion process mainly on a micrometer scale, okay? Because these are all just the micrometer scale substrate. So in this case, we begin to think, how about we work on try to work really confine the sodium nucleation and the growth process, try to go from the micrometer scale to a nanometer scale. So how we can achieve this is we try to find a two-dimensional host material here so that we can actually try to nucleate and plate the sodium between this two-dimensional layer in the nanometer level here. Okay, sorry, please excuse me. Okay, so here, this work is conducted by my prior postdoc, Dr. Luo, who also already a professor in the university in China. And Dr. Luo is an expert in synthesizing a very interesting material called the MXene. Okay, so at that time, we begin to think how we can actually take advantage of this two-dimensional layer of material to try to control the sodium nucleation and the growth material between the 2D layer of MXene material. So here I gave two examples of his work. So this work is we try to enlarge this interlayer spacing of the MXene material. Okay, so so in this case we use a surfactant. So this is we call the titanium carbide MXene-based material. So it's a two-dimensional layer material, very similar to the structure of graphene. So we enlarge the interlayer spacing and we dope the interlayer spacing of the material with some tin-based complex here. And then in this case, when we try to do the sodium nucleation and the growth process, because tin can actually easily alloy with sodium easily, so the sodium will begin to first plate within this interlayer, and then eventually it can grow around all these MXene islands and realize a very a smooth sodium deposition process. Okay. Okay. So here, just to show you, SEM image show that this is the MXene-based material, and eventually we reach a very flat sodium plating process without any dendrite or multi-sodium formation here. So further, like Dr. Luo also tried to improve this design by doing some nanostructure design within this interlayer. So he actually tried to grow some very interesting nanowire within this MXene layered material. So in this case, we actually achieve a better performance compared to the previous case, because once we grow all these nanowires, we actually get a 1D, 2D hybrid nanostructure. So all these pearl structure can actually help to induce the sodium nucleation within the interlayer spacing, and then eventually we also achieve a very smooth sodium deposition. So I did not put the electrochemical performance here, but experimentally, we do actually achieve a better electrochemical performance compared to the previous MXene design. Okay. So for the sodium metal case here, I would like to just use one last example here. So this work is collaborated with Dr. Hotier, right there. And we have formulated a sodium electrolyte, especially for sodium metal electrode that can work at a low temperature battery system. So we actually find a very good salt. This is called, I'm not going to say the full name, so which is really a long name. So we just call it the sodium OTF. So we find the sodium by the DFT calculation, and also combined with our experimental result, we find that the sodium OTF turns out to be a very good sodium salt combined with two organic solvent. One is, we call it a cyclic ether, another is a cyclic ether. So we combine the two ether-based electrolytes plus the sodium salt, and we actually formulated the electrolyte that can thermally stable down to the DSC. This is the DSC graph, thermally stable down to 150 degrees Celsius. And we also find that the electrolyte resistance, so if you look at the blue curve here and the red curve here, so you find that with decreasing temperature, so the internal electrolyte resistance have a very small change, even down to minus 80 degrees Celsius. So we find a very good electrolyte formulation. So the main reason here actually revealed by the DFT calculation is we find that the sodium ODF actually have a moderately high reduction potential versus sodium metal. So in this case, so this two green one is the NaOTF salt, another is we call it the NaPF6 salt. However, the NaPF6 has a very low solubility especially at low temperature, so it doesn't really work for low temperature battery. So we find that the OTF has a good solubility, and also in terms of the calculation, we find that it actually have a good reduction potential. So this salt can actually decompose first compared to the different solvent used in the electrolyte. So in this case, what here means, once the salt decomposes, it can form some inorganic protective layer, which is mechanically and chemically more stable compared to the organic species generated by the solvent case. So in this case, we find this very good formulated electrolyte specific for sodium metal targeted for low temperature operation here. Okay, so that's all I want to say for the on the anode case. As I mentioned that in my group, we have worked a lot on the sodium-based battery. Here, I want to change the topic a little bit, use maybe 5 minutes to talk about our effort, how we address the cathode, on the cathode and how we address the sodium-based battery system. I want to use 1 minute to talk a little bit about the background for this sodium-sulfur battery I mentioned in the, I think in the third or second slide. So sodium-sulfur battery, as I mentioned, is a very good emerging sodium-based battery technology because of the high theoretical energy density. It's also because the material used here, the cathode material, is a sulfur-based material. So compared to the conventional lithium-based, for example, the lithium cobalt oxide in our current lithium-ion battery, it has a very high theoretical capacity. And in terms of cost here, so you can see sulfur is very low cost in abundance. So that's why this battery system has been drawing a lot of attention in the past 5 years. So here I want to show you a sulfur pile that has been recovered from petroleum. So this is, we call it the sulfur pyramid, just to show you that how abundant and low cost the sulfur material can be. So as you can see that for the sodium sulfur battery, the anode one, so we talk a lot on the sodium metal case. So the cathode is composed of a sulfur or sulfur-based cathode system. So for this battery system, there are a lot of challenges. I talk about the challenges from the anode side. So on the cathode side, there's a series of challenges here. So one thing I specifically, including the low ionic or electronic conductivity, is because both sodium and sodium sulfide, they have a low ionic and electronic conductivity, which is not good for the battery performance. Another thing is during the discharge, the electrochemical discharge or charging process, we have something we call the solid-liquid-solid phase transition. It's because the initial, if we start with the solid sulfur, during the discharge process, it will transform to something soluble into the electrolyte. We call it the polysulfide. So we have a solid liquid, and eventually this polysulfide can come back to this sodium sulfide phase as an end discharge product. So we have a solid liquid back to a solid phase transition. So this is not a good phase transition for the battery performance, because once you have this something that can be dissolved into the electrolyte, the intermediate products, you will actually have a loss of active material, and also in terms of from sulfur to sodium sulfide, you also have a very large volume change in terms of the sulfur electrode. So in the past 6 years, we have developed a couple of techniques to try to address the challenges of the sulfur cathode. For example, we have developed some, For example, first we have developed some in situ Raman technique to try to probe the electrochemical reaction mechanism for the sodium sulfur battery, and we also try to synthesize some solid sulfur-based cathode and to try to realize a high capacity solid sulfur-based cathode material. I would like to point out this interesting material here. So this is something we call it a coral-like sodium sulfide cathode. So this is a coral picture, and this is the structure we synthesized. So you can see it looks very like a coral, so that's why we named this like a coral-like sodium sulfide cathode. And by using all these techniques, we actually have achieved a much better sodium sulfur battery performance compared to the existing literature. But I want to just use like a couple of minutes to highlight our most recent work is instead of starting work on a solid-based cathode material, so we have work on something we started with a liquid material. So we call it a sulfur catholyte. So catholyte just means a liquid cathode material. So in this study, the idea we have here is to instead of starting with a solid sulfur-based material, so you can see here, so this is we call the sodium polysulfide with different chain lengths right here. So we take advantage of some phosphorus complexation reaction. Okay, so we introduce phosphorus into the sodium sulfur redox reaction, and we actually achieve a series of, we call it a catholyte, a liquid complex material that can be dissolved into a different solvent system. So, and for this material, the material actually have a very long name, so it's called the sodium phosphorus-thiazide complexes. Okay, so which we use MP2S5 and Na2S. So we use this formula to indicate this a series of new complex material we have synthesized. So, and we also be able to control the molecular structure of the material by tailor this material from two different dimensions. And one is we can actually control the chain length right here, and we can also control the molar ratio between the phosphorus-based compound and the sodium-based compound here. Okay. So why we work on this is, as you can see that, as I mentioned, we try to prevent this cyclic liquid-solid phase transition in the electrochemical reaction of a sodium-sulfur system. So we want to start with a liquid material and end with a liquid material. And there's no solid material precipitated out during this electrochemical process here. Okay. So here I just want to briefly mention we have done a lot of work by collaborating with Professor Weiyang at Stanford. We actually have to try to figure out what's the molecular structure of this new series of complex material. So this is we have really went through a long way to eventually identify the molecular structure of all these explored complex material, because nobody has ever really synthesized this material before, and it's very hard to identify their molecular structure. So you just want to skip this and show you this is based on the DFT calculation and combined with our AMR analysis. We eventually proposed this, what's the molecular structure and what's the complexation mechanism of this new series of complex material here. So you can see this is what the structure we proposed right here. I'm not going too much detail because, as you can see, that it's relatively complicated and hard to explain in a short amount of time. So I just want to show you the electrochemical performance when we try to use this material for the sodium-sulfur battery. So I want to highlight something if you bring your attention to look at this figure here. So you can see this is, for example, a conventional liquid cathode material we use is the black curve. And then compared to this red curve we developed is the complex material. We find that the electrochemical potential is much higher compared to the conventional case. So this is a good thing because the higher voltage you can get for a battery system, the higher energy density you can actually deliver. Okay, so in this case, for this new complex material, we actually can achieve a higher capacity, and we also can achieve a higher voltage compared to a conventional case. So this is, I would like to just show you that this is based on DFT calculation. We do compare the theoretical calculation with the experiment. We do see that both based on theoretical calculation, the reaction potential of this complex catholyte, it does have a much higher potential, I don't want to say much, does have a higher potential compared to the conventional case. So I would like just to want to show you one slide right here, because one of the reasons we want to work on the catholyte material is we try to use this catholyte material for the low temperature application here. So as you can see that because we actually avoid this cyclic solid liquid and solid phase transition, so in this case we actually boost the kinetics of the battery material for low temperature application. So especially I want to bring your attention for this capacity versus cycle number. So you can see this is at minus 40 degrees Celsius. So using this material, we're still able to achieve a very stable cycling performance over 300 cycles here. Okay, so I think I'm running out of time, so I just want to summarize. I will talk a lot about our strategy of stressing the sodium metal anode, and I just use one quick example here to demonstrate our effort to address the sulfur cathode material. So at last, I would like to thank all my group members, and especially my 3 prior postdocs who already have their independent group they're in China right now. And also, I would like to thank my collaborator and my graduate student. I also would like to thank the funding agency from NASA. This is AFSR, the Cold Region Research Engineering Laboratory, NSF, and the Urban Institute. And also, I would like to thank my startup funding from SARE and the Dartmouth Innovation Program. So thanks for everybody's attention, and I'm sorry, I hope I'm not running over time, and I'm happy to take any questions.